Yeah, so in the previous chapter, we learned the general theory, the combinatorial models for the moments of orthogonal polynomials. And when we study orthogonal polynomials, there are roughly two ways. Study general orthogonal polynomials or study specific orthogonal polynomials. There are many well-known orthogonal polynomials, and so in this chapter, we will study well-known orthogonal polynomials, most often called classical orthogonal polynomials, using the general theory that we learned in the previous section. So, and note that but whenever we have a family of orthogonal polynomials, there are several ways to define the polynomials. There are several ways to define, say, OPS. So first, we can just give an explicit formula for the polynomial. So coefficient, say A and K of the polynomial, nth polynomial. So because it's a polynomial, you can write down this as a linear sum of things like this, right? So if you know the coefficients, then you know the polynomial. So this is one way. And a generating function for the polynomial. Namely, if you have a formula like this, Pn, t to the n, and greater than or equal to 0. Or sometimes we consider generating functions of this form, often called exponential. So this is called exponential generating function. It's called ordinary generating function. It's called ordinary generating function. It is called exponential generating function. So once we know a formula for this, for instance, like exponential, like t squared plus, I don't know, say, if we know that this is t plus t squared over 2, something like that, then we know exactly what these coefficients are. So we know the orthogonal polynomials. So there is also a way to define polynomials like this, and moments. The moments completely determine the linear functional, and once you know the linear functional, we know the orthogonal polynomials. So it's also possible to define polynomials using this, or the three-term recurrence coefficient. Coefficient, which we often denote by bn lambda n. So just to recall, we know the orthogonal polynomials must satisfy three-term recurrence like this. And if we know these coefficients, the three-term coefficients, then that means we know the recurrence. So the initial condition is always like -1 is 0, 0 is 1, so we know the polynomial. So sometimes we will give an orthogonal OPS using just by an explicit formula, or sometimes just generating function, or sometimes moments, or sometimes just Bn and lambda n. And any of these will completely determine the polynomials. So our first example will be Chebyshev polynomials. So it's one of the simplest orthogonal polynomials, Chebyshev polynomials. And actually, there are two types of Chebyshev polynomials. First kind. We will first consider the second kind, because that's slightly easier. So recall the Chebyshev polynomial of the second kind. Are defined by I'm gonna define this using explicit formula, which you have seen before. So x is cosine theta, so n greater than or equal to 0. So for every index n, we know explicit formula for the polynomial. So the polynomial, this family is determined, and we know that they satisfy this recurrence relation. So we also know the three-term recurrence. N greater than or equal to 0, and we will always use this this convention, like this. And from calculus, we know we know from calculus these they must satisfy this orthogonality. The measure is like this. Is pi over 2 delta mn, right? So in other words, this sequence of polynomials is an OPS for L. But let me define L, where, but we want this to be 1. So instead of using this, we will divide this by this, so that we get L of 1 equals 1. So L of fx defined to be 2 over pi minus 1 to 1 fx 1 plus 1 minus x squared 1 over 2 dx. So if we define our linear functional L in this way, then they are orthogonal with respect to this measure. Okay, that's the definition of the orthogonal polynomial. And note that L of 1 equals 1. But we prefer monic orthogonal polynomials, but this is not monic. But we know how to make this monic, right? You can just divide every polynomial by its leading coefficient. So to make this monic, u and x has coefficient 2 to the n. So for all n greater than or equal to 0, so we define the monic Chebyshev hat, let's use the notation hat, is nothing but u and x. We just divide this by 2 to the n, so it's minus 2 to the minus n. Minus 2 to the minus n, yeah, for n. And because we divide this by 2 to the n, we can get a recurrence from this. If you divide both sides by 2 to the n plus 1, then we get the recurrence like this. So if we divide a three-term recurrence for un by 2 to the n plus 1, then we get in our form x minus 1 over 4 x for all n greater than or equal to 0. Okay, that means bn equals 0, lambda n is always 1 over 4, which is simple. Okay, and because this is just a rescaling of this, they are still orthogonal with respect to that linear functional. U tilde is an OPS for L, right? The linear functional that we defined before. And what is the moment? Nth moment is L of x to the n, that is 2 over pi minus 1 to 1 x to the n 1 minus x squared 1 over 2 dx. But if you compute this, this is just an integral, so we can compute this using just your knowledge in calculus. Then you get mu n is actually 1 over 4 to the n cn, where cn is the even moment is non-zero, but odd moment must be 0, because if you look at this, if n is odd, it's a symmetric or it's an odd function, so it's going to be 0. Where this is the Catalan number, which is this. This can be proved using just calculus. But we can prove this immediately using the formula, the combinatorial model for the moment. We know combinatorial recall, the moment is generating function for all Mochkin path, the weight sum of the Mochkin path, where this is the product of all the weight of the steps, and when we have like height I, every up step has weight 1, and horizontal step has weight bi. A down step starting at height I has weight lambda I. Okay, so but in our case, this is a 0, and this is always 1 over 4, right? That means mu n equals, you cannot use horizontal step. What is the Mochkin path without horizontal step? It's a dig path, exactly. So this is sum over all dig path of length n, but the length must be 2n, otherwise you cannot, if you have to come back to the x-axis, the number of up steps and down steps must be the same, so this must be even, unless it's going to be 0, just like this. And what is the weight? Weight is exactly the number of down steps, which is half of this, so it's 1 over 4 n over 2. So mu 2n equals pi dig path 2n 1 over 4 to the n, right? And mu 2n plus 1 equals 0. But what is the number of dig path of length 2n? That's the Catalan number. So this is how we can prove this immediately. So we didn't do any integration over here. Just using only the combinatorics, we can prove this directly. Okay, now, so this is Chebyshev polynomials of the second kind, but we can also do similar things for Chebyshev polynomials of the first kind. It's slightly more complicated, but not much. So the Chebyshev polynomial of the first kind, if you remember, these are defined by this. T and x is just a cosine n theta, where of course x is cosine theta. And we have this orthogonality. The measure is slightly different, minus in this case. And this is 0 if m different from m. This is the orthogonality. And actually, if they are equal, it's going to be pi. So I think I can just write down the pi. Yeah. Then, so we want Tnx is an OPS for L, but we want L to be linear functional with L of 1 equals 1. So to do that, L of f of x is defined to be 1 over pi of that integral. if we define the linear functional in this way, then they are orthogonal with respect to this linear functional. And what is the moment? Moment is L of x to the n. So it's 1 over pi minus 1 to 1, x to the n, 1 minus x squared minus 1 over 2 dx. And again, if you compute this, you will get you can get something like this. Using calculus, we can prove things like this. 4 to the n, to n n. Again, very much like a combinatorial number. So 0, and this is 2n choose n. But the question is again, can we prove this combinatorially? That's the goal. But again here, we have to make this monic, and we have to find the 3-term recurrence coefficient. So how can we do that? We already did it. So the monic Chebyshev, first kind, is defined to be T0 is 1, but Tn is this, but this has leading coefficient 2 to the n minus 1, so it's going to be 2 to the 1 minus n for n greater than or equal to 1. So the difference here is that before, for the second kind, we always have this. But in this case, we have to deal with this separately. So that's why it's a little more, we need extra work here. And in fact, we also found, recall, we did this before. We have a 3-term recurrence like this. Bn lambda n, where Bn is always 0. Lambda n, there are two cases. 1 over 2 if n is 0, and 1 over 4 if n is n greater than or equal to 1. So it's always 1 over 4 except n equals 0. Okay. So now how can we find it? Find the moment. The moment is generating function for all Matchkin path n weight of pi. Then because Bn equals 0, we have no horizontal steps. So you must have dict path only. So it's going to be 0 unless n is even. Okay? And so mu 2n plus 1 equals 0 because no horizontal step. Horizontal, yeah, I mean, you may consider horizontal steps, but their weight will be always 0, so you can just ignore them. Now, what about the even case? It's the same thing as just considering dict path of length 2n. But what is the weight? It's slightly different before because it's not always 1 over 4, but we have to deal with this separately. But what if you just pretend that lambda n is always 1 over 4, just like before? So that means 1 over 4 to the number of down steps. Down step is always n. There are n up steps, n down steps. So if we have the same situation as before, we would have things like this. But it's not quite correct. We have to make it correct. We have to multiply something. We have to multiply 2. 2 to do, let's say a of pi, where a of pi is the number of down steps touching the x-axis. Okay? Why is that?
One is 1 over 2.
Hmm?
N equals 0. N equals 1.
Ah. Oh, yeah. Sorry about that. Yeah. Lambda index starts from 1, so it must be 1 and 2. Sorry about that. Yeah, you have to be careful. Beta B index Bn starts from 0, but lambda always starts from 1 because Bn can touch, the horizontal step can touch the 0 level, but lambda always, the lowest lambda is lambda 1. So yeah, this is right. Okay, so let me explain a little more about that. So for example, maybe I can just give you an example like this. Example. Let's consider a step like this. Like that. And if pi is this, what is a of pi? Number of steps touching, down steps touching x-axis. So this, and this. So it's going to be 3. So the we must multiply 1 over 4 for this down step, and 1 over 2 for the down steps touching the x-axis, but other down steps have weight 1 over 4. And because we said this is 1 over 4 to the n, which is the number of down steps, we pretended they are all 1 over 4. So to compensate that, we have to multiply 2 to the a pi, which is 3 in this case. Then we will have this exact weight, the correct weight. So what do we need to do now? So we need to show mu n equals 1 over mu 2n but this we need to know this, some pi dig path 2n 1 over 4 to the n 2 to the an a pi, right? This is what we want to know. But now we can cancel this, so we need to prove this claim. Sum over all dig path 2 to the a pi, a of pi equals 2n choose n. Okay? But there is a nice trick. So when we see things like this, 2 to the something, that means for every down step touching the x-axis, we have 2 choices. We can understand in this way. We have 2 choices for this, 2 choices for this, and 2 choices for this. And for each choice, let's say that we either color this red or not. So proof. So what I'm saying is that 2 to the a pi equals number of let's say colored dig path from where a colored dig path means, here a colored dig path means a dig path where every down step touching the x-axis may or may not be colored red, say. So that means we have 2 choices. We give 2 choices, and that will come to this. So for example, let me example. we can forget about these weights. For example, we have a choice to color this red or not. We have two choices for this and two choices for this. And let's say we colored this and this. So there are 8 possibilities for this, but we say we color this and we didn't color this and we color this. And we want to show that this number of colored dict path equals 2 and choose n, but this is like choosing, how can I say? This is the number of ways to arrange n up steps and n down steps without any restrictions. That means here, this is 0, 0, 2 and 0. So we have like n up steps, let's say n ups, n downs, right? And what I'm going to do is whenever we have a down step like this, you look at the first, just imagine that this is like a mountain and then you have a tunnel like this. So you see this, if you make a tunnel, then this will see this up step. What I'm going to do is I'm going to flip this mountain about the x-axis. If the down step here is colored red, so flip. Flip the part with red color. Like this part will be flipped, but this part will not be flipped. This part will be flipped. So we will get something like this is flipped, so it goes like this. This is not flipped. This is flipped. And you see, you can, in this way, you can get any path from here to here. Any path using n up steps and down steps. And the number of path here without any restrictions using up steps and down steps is exactly 2 and choose n, because you just select the positions for the up steps among the 2n positions. Actually, that's the proof. That's basically the proof. This is a bijection. Bijection, because whenever you have a path like this, you can just flip things below the x-axis like that, and then you mark these down steps red. There's a bijection. It's a 1-to-1 map. And that's the proof, basically. Yeah. Is everything okay? All right. So that is for the Chebyshev polynomials. Now let's look at Hermite polynomials. So Hermite polynomials are probably the most well-known orthogonal polynomials, I guess. At least one of the most well-known, yeah, well-studied objects. And because of that, because they have been studied by many people in different groups, in physics and mathematics analysis and probability people. So if you have a mathematical object like that, the problem is they all use different conventions. So we have to. So sometimes if you study orthogonal polynomials, one somewhat annoying thing is to make things into your convention. But they are all kind of straightforward, but it needs some time. But yeah, let's see. So the Hermite polynomial, let me define Hermite polynomials. the Hermite polynomials denoted by capital Hn of x. The Hermite polynomials are defined by, I'm going to define this using three-term recurrence. So this is 0, this is 1, and hn plus 1 x equals 2x x hn x minus 2n hn minus 1 x for n greater than or equal to 1. 0. I chose this definition because this is the first one appearing in the Wikipedia. But I think this is probably more people use this, especially in physics. Yeah. But we will see how to change them. But for us, we always prefer monic orthogonal polynomial. So, but they are not monic. So, but we know how to make them monic. So, the leading coefficient is always 2 to the n. The leading coefficient of Hn is always 2 to the n. So we can simply multiply Hn by 2 to the minus n. So define h hat sub x of x, n of x equals 2 to the minus n hn of x. Then we can get a return recurrence just by dividing both sides by 2 to the n plus 1. So let's say this is equation 1. Divide 1 by 2 to the n plus 1. Then we get this divided by 2 to the n plus 1, so we get just a hn plus 1 hat. And here it's going to be n plus 1, but 1, 2 will be cancelled, so this is hn hat. So, and here n over, you divide this by 2 to the n plus 1, so you divide this, and you have one of these, it should be n minus 1, so you have 1 over 2 left. We have something like that, okay? We can work with this because it's a monic orthogonal polynomials, but we will modify a little further because we want to count the things. But whenever we have a fraction like this, we have to multiply, like just like we did over here. We have to multiply 1 over 4 to the n, something like that. So we want this to go away, and then we just want orthogonal polynomials with recurrence just n. But how can we do that? This is already monic, so we cannot really change anymore. But there is a way. There is a way to rescale things so that we make things as we want. But let me give you an example, lemma. So lemma. So rescaling OPS. So the fact is, this kind of constant in the denominator can always be scaled away. So suppose is a monic OPS with return recurrence given in this way. I'm going to use the usual initial condition. Okay? And the idea is we modify x together. We change x by something. So x divided by something. So let Tn Pn tilde to be, we change this x over a. But this is not monic anymore. But what is the leading coefficient? 1 over a to the n. So if you multiply a to the n, it will be a monic. Okay? Then Pn plus 1 tilde x equals, this is similar to this, almost similar, except we multiply a here, multiply a squared there. X a squared lambda n Pn minus 1 tilde, like that. Proof is just one line. Just substitute x by x over a, and multiply both sides a to the n plus 1. So that's one line, proof. Substitute x by x over a and multiply a to the n plus 1, then that's it. That will give you the right formula. So quite easy. So we want to move this away. We want to scale this away. Then how should we change the axis? This must be 1 over 2 must be a squared. So the thing is, definition. The rescaled Hermite polynomial, which we will denote by h tilde, are defined in this way. Square root of 2 to the n h hat sub n x over square root of 2. Is that right? I thought. According to this lemma, we will have to multiply. Yeah, I think this is not true. I think this should be minus. Yeah. According to this lemma, square root of 2 x. This seems better. Is that right?
I think
the previous one is correct?
Yeah.
Wait a second. This we want. Oh, sorry. Yeah, that's right. Yeah, sorry about that. Square root of 2 to the n. Yeah, because we divide this by a. So yeah, sorry, I was confused. But anyway, if we define in this way, then finally we have nicest formula like this. So b is not there, so we don't have to worry about it. N h n minus 1 tilde x, where of course the 0 minus 1 is 0, 0 is 1. So this is called physicist Hermite polynomials, and these are called probabilistic Hermite polynomials. But we will use this because yeah, it's nicest. But they are really the same thing. So if you can do something with this, you can do the same thing with this. All we need to do is to modify things like this. So whenever you study orthogonal polynomial somewhere else, you will often see situations like this. You have something that, but you don't quite like it, then you will have to rescale it in this way. But eventually, you will be able to connect these two things. They are equivalent. That's why this is sometimes called Hermite polynomial. This is called Hermite polynomials. So when some people say Hermite polynomials, you have to look at the definition carefully because people use all kind of different definitions. But they are all equivalent in this way. Okay, now we will be focusing on this rescaled. So what is the moment then of the rescaled Hermite polynomials, R, which I'll simply write mu sub n. Then this is again in our combinatorial model, weight of pi. But we know that Bn equals 0, and what is lambda n? Lambda n equals n. So if Bn equals 0, you don't have horizontal steps, so it's going to be a Machkin path. We only need to look at a dict path. So again, mu n plus 1 equals 0, and mu 2n equals sum over all dict path of length 2n. Weight of pi. And in fact, if you compute this, then for small n, like mu2, mu4, and etc., you will see a clear pattern there. And in fact, this is going to be equal to, we will prove this later, today, but later today, 2n minus 1 double factorial, which has a very nice product formula like that. So we want to prove this. But the thing is, this is kind of similar philosophy as before. When we have sum over some integers, often we want to make a new model, like a labeled model, so that this is just a number of some object. Instead of adding numbers, we just want to count things by giving some more structures on the combinatorial interpretations. So this is how we define this. So the question is, what does mu 2n count? This is a positive number, so it must count something, but we want to know what those are. So here's the definition. Our Hermite history. This is Viennot's terminology. So Hermite history is just a dict path. Labeled dict path, basically. A dict path where every down step starting at height, say height k is labeled by an integer in 0, 1, k minus 1. And let me denote this by a set of Hermite histories. Two n comma 0. Okay. Let me use 2n just to make just so that we have the same number here and there. Okay. So what does that mean? So it's really just a labeled dict path. So suppose that we have a path like this. So what is the starting height? This is 1. So that means maybe it's too small. example is too small. Let's say the starting height. This is height 1, height 2, height 3, height 1, 2, 3. So that means we have a label here, but there is only one choice. We have to give a label 0. But here we have two possibilities, this or this. Here we have this or this. We choose one of these here. So once you choose labels, then that's a Hermite history. So for example, let me just give you a specific example. So if I choose, say, let me choose this and then choose this, and let's choose this, and like that. So this is a Hermite history. Then, from definition, it should be clear to you that this is the cardinality of the Hermite history. Is this clear to you? If you understand, if you understood all the definitions, then this should be clear. Why is that? What is the weight? Each down step of level, say level I, we have to multiply I. That's the same thing as, that means, but for each down step of level I, we have I possibilities. So this is exactly counting the number of, so basically this is the number of Hermite histories with the same dig path. So this, if you want, this is because it's the number of Hermite histories with underlying dig path pi. So, for instance, suppose that you fix this pi. How many Hermite histories are there? Here you have to select. You have to select one of these. So it's 1, 1. You have to. There are two possibilities. 2, 2. There are 3 possibilities. So you multiply all of this. That is exactly the weight. So if you add all the weights, that's exactly the number of all Hermite histories. Okay. So we know that this counts Hermite histories. But now we want to show that that number of Hermite histories is this. That's our next goal. But this number is somewhat familiar to us, right? We have seen this before. This is the number of complete matchings on two n vertices. Okay, this is actually number of complete matchings on 2n vertices. So if you have 2n vertices, then this has to be connected to one of these, which is 2n minus 1, and then the remaining one you have to connect with in 2n minus 3 ways, etc. So we proved this before. So, but let me define this notation. So let Cm2n be the set of all complete matchings on 2n. Then we know this cardinality is 2n minus 1 double factorial. So our proposition is there is a bijection. V, say Hermite histories to complete matchings. There is a nice and simple bijection like that. This can be explained best by example. Yeah, let me give you an example, then you'll be convinced that it must be true. So, example. This is Hermite history. I'm gonna label this by 2, 0, 1, 0, 0, like that. Okay? This is Hermite history. Then the idea is we're gonna create a complete matching on what is n here. So this is Hermite history. How many steps are there? 1, 2, 3, 4, 5. So it's going to be 10. We want to find a complete matching on 10 vertices. This 10 is the number of steps, right? So for each step, we're gonna create a dot. So here is that I'm gonna align them so that we have each down step or each step corresponds to one dot. Like that. You see, like that. So we have 10 dots here.
You skipped one.
Oh.
Step there.
Oh yeah. Yeah. It's too close to that. It's not a bijection. Now 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, so 10 dots. Okay. So what is complete matching? You want to connect them, all of them. So complete matching is like having 5 edges. So on edge, always on edge looks like this. Okay. So the idea is for an up step, I'm gonna create a half edge like this. Let's say this is opener and closer. Okay, I'm gonna okay. This is an up step, open, open, opener, and down step corresponds to closers like this: down, down, and up, down, up, down, down. Okay. Now, if we can connect all the openers with closers, then we will get a complete matching. And that will be determined, how we connect dots will be determined by these labels. So 2, when you see a label 2, you connect, this is a label, it has a label that means it's a closer. You have to connect this with opener. And this will tell you how many openers you skip from here. So we have 1, 2, 3 possibilities, but you skipped 2 openers. Skip, so you connect like that. Okay? Skip. So here, skip 2 openers, available openers, each position. And now here, you have to connect, but you skip 0. So you connect this with the closest available opener. So it's going to be this. And what about this? This is, you skip 1 opener. So you skip this and connect with the next available step, opener. And this you skip nothing, and you skip nothing. So in this way, you get a complete matching. And this is a bijection. If you think about it, you will be convinced that it's going to be a bijection. But because, you know, you just look at the local configuration, and then each time you see where you connect the dot. So the local configuration will determine the shape of the dig path, and how you connect the dots, how many openers you skipped each step, that will give you labels there. So it will be a bijection. And the label is less than equal to the height because the height is exactly the number of available openers. So height of the starting point of a down step is basically the number of available closers. So that's the proof, basically. So now corollary is mu n, mu 2n is the cardinality of the Hermite histories of length 2n. But this is the same as the number of complete matchings because we have a bijection. But this is 2n minus 1 factorial, double factorial. So in other words, this is the number of complete matchings. So Hermite polynomials are the number of complete matchings. So actually, maybe I can even say it like this. Let me write it this way. Or in other words, matchings on n. You can, if n is odd, there is no complete matching, so it will be 0. But if n is even, that is exactly the number of complete matchings on 2n, so you can write things like this. So for Hermite polynomials, the moment are counting complete matchings. Okay. Okay. Yeah, I don't think I have enough time to cover the next section, but so let me just tell you the story that what we are going to do next. So classical, when we say classical orthogonal polynomials, then usually they include Hermite polynomials and Charlier polynomials, and we saw this earlier in the semester, and Laguerre polynomials, and also Jacobi, but we will not consider Jacobi. We will consider the 3 of these. This can be studied similarly, but weight is more complicated, so we will look at this. And the nice thing is they all have moment. Their moment count things. So here we know there's a number of complete matchings. Right? Moment is a moment mu n, let's say mu n. And we will see later in the next subsection, Charlier polynomials, their moments also count something, and it's number of set partitions. On n. So we, yeah. And for Laguerre polynomials, it's also number of permutations in this case. So they all have very nice combinatorial numbers. So we proved this, and yeah, we will prove this in the next class. Okay, thank you for your attention, and I'll stop here.